figure we want to do one more just for giggles and point out a couple more things. Pretty much all the regressions we've done, I think including the ones in the problem set, have year as the predictor, as the x variable. That certainly does not have to be the case. When you have year as one of your variables, and that's what you're plotting, year pretty much always will be your predictor because time does its own thing. We don't expect the number of salmon in the pilot tributary to affect years. It's years that has an effect on salmon, or has the underlying control for salmon. But it is also perfectly fair to use correlation and regression analysis to answer questions about relationships between two variables when we don't necessarily know or even think that one variable is controlling another variable. So we happen to have numbers of salmon in two different tributaries here, and it is, again, perfectly legitimate to ask the question, well, is there a relationship between the number of salmon in the pilot tributary and the number of salmon in the East Fork tributary? Now, these pilot tributary may not in any way physically be attached to the East Fork. Water from this tributary may not touch this. We may not have salmon that can swim in between the two. But we could imagine a case where some other variable may control the number of salmon here and here. And we want to know whether or not that's the case. We want to know whether or not changes in salmon in the pilot tributary are following the same pattern as changes in the East Fork tributary. That is also and still a correlation kind of question. We also note that there is a blank space here in the East Fork tributary data. Perhaps for whatever analysis we're doing, we really need a full data set. We need a value here, and we can't just, or don't want to just delete out this row. It is important to us to have an estimate of this. Well, if there's a good relationship between what's happening here and what's happening here, we have data in the pilot tributary. So we could use this value and the regression equation to say how this value relates, or how this variable, how number of salmon in the pilot tributary, correspond to the number of salmon in the East Fork tributary, and use our regression equation to take what we do know to predict, to interpolate a value that we don't know. And we'll get our kind of best estimate using linear regression on how many salmon should actually be in this number. And then we can go ahead and have a full data set to do whatever it is we actually want it to do. So all of the steps are pretty much going to be the same, except we don't have year on the x. We're going to have pilot tributary on the x. And I'm specifying this is going to be on the x so that later we can predict this blank value in the y. We always do our predictions on the y variable using the x variable. So x always has to be known, and y is what we'll end up solving for. Same kind of thing. It's a good idea, always a good idea, to plot your data. Don't have to worry about the Corel functions or covariance functions in Excel. We'll just have plots do things for us. I take the kind of longhand approach. Instead of highlighting things ahead of time, I go straight to the data here and plot things manually, so I know I'm selecting the correct things and in the order I want them to be. Don't care about series name, series x values. So there is a missing data point here. However, and this is one nice thing about Excel, we can actually highlight all of the data, and Excel will just skip over this point when it comes time to do the plot. We don't have to fill in a missing value, although you could if you want. You could put an NA or missing or some other code, as long as it's not a number that Excel is going to try and plot as a number. I'm just going to leave it blank because this is a small data set and I can see that it is blank. Again, it auto-populates for that equals bracket 1 that we will delete out of the way. So we'll highlight all of our data. You can see we have data points, so even though there's the blank, things still worked out. Another alternative that would be okay from a data analysis standpoint is to ignore these first years and maybe just start at 2002 and do your regression and correlation analysis based on 2002 onward, where we had a full data set, and then we could extrapolate one step backwards. That would be also acceptable, but no particular reason why we would have to do that. In fact, there is something to be said for sticking to an interpolation and including the years beforehand in the off chance that prior to 2002 the data did something really weird that we weren't aware of. So we'll stick with this. We are done with this plot. Get rid of the title because it just takes up space. Will be good, and add some X labels. And here we don't want to get confused. So our X we said was going to be the pilot tributary, so we'll just leave it at pilot. And the Y is going to be the East Fork. Did I spell it right? Yes. East Fork tributary. Okay, so there's our data. Looking at it, well, it doesn't look great. Ideally, we would have seen something kind of like this. That was just a really good straight line. Maybe even something that did kind of like that. But we can see as time's increasing, we're almost getting more and more scatter over time. So that's not great. We'll keep plugging away and see what happens. The next thing we should do is go plot our regression line. And we'll do that right-clicking on a data point, add to trend line. It's already linear. We can see, yep, there it goes. It doesn't go through 0, which is fine. It doesn't necessarily have to do that. Our data, we were kind of eyeballing it, saying that, yeah, it looks like it increases, maybe not well, but it increases, and our best fit, our linear least squares regression line, is also increasing. So that matches our expectation. Notice that the best fit line does not go through the lowest point, which I might have expected it to. So it's a good thing we're letting these statistics fit that line for us instead of me fitting the line for us. We do not want to set the intercept, but we would like an equation, especially since we're going to do some interpolation later. And we would also like to do the r-squared to make sure that our slope is significant. Because if it's not significant, there's really no reason to do our prediction, because that line might as well be 0. We can see even if it is a significant slope, the r-squared is 0.05. So our change in the pilot, our piloting x variable, only explains 5% of the variation in the East Fork counts. 5% is not very much, so whatever we get is going to be a super rough estimate at best. It may be the best we can do, but it's not going to be good. So that's r-squared, just like before. We want to go check a p-value and see is it even worth looking and doing our interpolation or anything else. So we want an r next, and r is going to be the square root of r-squared, which according to this right here is 0.05. Well, I'll stick the 1 in there just for grins, probably not necessary. R will always be greater than or equal to r-squared, and it is, so that's again our double check that we correctly calculated an r and didn't accidentally take a square root of r squared, take a square of r squared instead. The slope is positive. Looking at the line, the slope is positive based on the slope of the linear regression equation, so r also stays positive. We do not need to add a negative sign in this case. We need to calculate a t-score next, so we can ultimately calculate a probability, a p-value. And this is going to be equal to r, which we have here, times the square root of n minus 2. We still have 22 pairs of data, minus 1 for the header row, minus another one because we have that blank row. And so this is not actually plotted. So we have 21, so we have 20 rows of data, minus another 2, so 18 degrees of freedom. Now I spelled it out last time, let's just spell it out again. 20 minus 2 degrees of freedom. And then we have that, and another square root of 1 minus r is still here, squared, and close that parenthesis, close another parenthesis for the denominator, and we get a number which is also small, but not a horribly ridiculous number. If this was a 2000 or 0.0001, then I might expect that I had a typo in there. This is kind of in the range of t-scores that we've seen previously, so that is heartening. Notice that pretty much each of these steps I'm doing some sort of proverbial kind of back of the envelope double check and make sure I'm not messing things up. Our p-value, we use again a two-tailed t distribution to do. So t dot dist, because we have a distance in the form of a t-score, and we want a probability. This is a two-tailed test. Absolute value we don't have to worry about because it is already positive. We don't even have to type it in. We'll just do that. And n minus 2, I've already forgotten what it was. I think n was 20. So we'll spell this out again. 20 minus 2. Like that. And we see our p-value is well above 0.05, kind of the default. It's also above 0.1 or really any other significance level, an alpha, that we might want to use. So even though we have a positive slope, our p-value suggests it is entirely possible to get a slope like this if the true slope were 0. Now what we're seeing could just be by chance. So for our purposes, that's kind of disappointing, because that means, yeah, we have a regression equation. This is our best estimate, but there's really no reason to go ahead because this equation might as well be y equals 0. Well, y equals the mean is actually what it is. For the purposes of just teaching, I guess, let's keep going ahead anyway and work through the rest of it. So we know we shouldn't do this because we do not have a significant p-value, but we'll go ahead. Perhaps we just really have to get a number. And the linear regression is still our best approximation of a number, even if it's not good, and perhaps even if it's not appropriate. So how would we do that? In this case, we have the regression equation already, and so we want to solve for our missing value. And we can do that directly. So y is the missing value because we've plotted it this way. This is the east fork variable, and we want to predict an east fork value. That's where our missing data point is. So there's our y. So this is going to be equal to, and we're just following the equation here, 0.0064. And then it says we have to multiply times x. Well, the x that corresponds to our missing data point is that one right over there. And then this equation says we have to add 2839.6. Okay, so that is our best estimate of that missing data point. Because that missing data point falls within the range of our previous data, as in we had x's on this side, we had x's on that side, this was an interpolation, which if we can interpolate instead of extrapolate, that is what we would prefer to do. Because it gives us some confidence that weird things didn't happen outside of our data that we're not aware of. Having done our regression, we should then be good, even though we're already not being good by doing regression analysis with insignificant p-values. We should do a residual analysis. Look at the residuals. We do our fit and make sure that our fit doesn't have weird things. So I'm going to insert some extra rows and make some room here. And we need the residuals. So in order to do that, I need some predicted values. The predicted values follows the exact same, if I can get that over, follows the exact same format as we have here. We predicted a y value. Now we want to predict more y values, and we want a new y value for every x value that we have. So we're going to copy this equation over. 0.0064 is equal to 0.0064 times x, and then we're adding some number over here, 2839.6. 2839.6. So there is our estimate, and we'll drag that down. So now we have estimated values for, or estimated y values, east fork tributary, for every x value. These predicted values are effectively they make up this line. So we have now calculated the predicted y value for this data point. And so we can subtract the two to get that residual. And we've calculated the y value for this point in the line that corresponds to this observed data point, so we can get a residual, and so forth. So we'll have a residual for every point, every x value, every point on our line. So that is the next step. Let's do the residual. And residual is the observed minus the predicted. So there is our observed, there is our predicted, and so we will drag that across. Also, I'm going to go back to this blank space, because remember, we don't have an observed value, so Excel is going to treat that as a 0 right now. And we can see it is a rather large number, 3615, or 0 minus 3615 is minus 3615, but that's not a real 0, so we're going to skip it. We don't want that affecting our numbers. And then we want to plot the residuals. So under the hood, in the background, Excel was doing this kind of thing to create that best fit line, the sum of the square of the errors. So here is the errors that we just calculated, and then we would do the sum of the squares and try and minimize that. We don't have to worry about that. Excel has already done it for us, but what we would like to do, and maybe we'll just do this down here, is create a plot of the residuals. So we want to make sure that our ultimate plot doesn't have any weirdness in it. So let's do that. We want to select some data. We still only have one series, so we don't have to worry about series names. Our x values is actually x values, which is not East Fork tributary, it is Pilot tributary. And our y values, after deleting that default one there, is the residuals that we just calculated. So we'll click OK here. So ultimately, we want our residuals to be centered around 0, to have, in general, equal numbers of positive values and equal number of negative values. And we don't want there to be any pattern in the residuals. So we don't want there to be an increasing proportion of one of them over the other over time, or cyclical patterns or anything like that. So we look at our data. What do we see? Well, it's also not great. 0 is kind of in the middle, but we can see we're a little skewed on the positive side. So we don't really have an equal number of points above 0 as we do below 0. Perhaps most disturbingly is as we move over into the x, our range is getting higher and higher. So the residuals are getting larger and larger as we're increasing in x. That has a fancy name in statistics because it appears all the time, heteroscedasticity, and it's not something we want to see. So this kind of residual plot shows us that not only is our p-value not good, so we should not perform a linear regression, but the plot of our residuals shows that we are violating one of the assumptions of regression analysis, specifically that the variability, the residuals, need to be constant as we increase the x, and they are not doing that. So for two reasons, we should not do what we did, and we should not be trying to use the Pilot tributary numbers to predict East Fork numbers. So hopefully that was kind of useful, at least as far as here's some buttons to click in Excel and some things to consider when making plots, and yeah, that's that.